I'll move in a uniform magnetic field. Let me move with a constant speed v in uniform magnetic field. Let the length of this conducting rod be L. It's a iron rod. Now let the B bar be the strength of the magnetic field. Then will there be any potential difference set up across the ends? So let's assume that a positive charge, of course, there won't be displacement of positive charge. In fact, it will be electron only. To make that negative signs little bit, to avoid that negative sign, I'm taking the hypothetical positive charge. If the rod moves, what is the state of this electron, or it's like a positive charge or electron? It will be moving randomly inside this. So there's a random motion. And as the rod moves, what happens? Due to this will be ordered motion. Now, what will be the Lorentz force due to that random motion? Will be zero, no? Because what is the net displacement due to random motion? Will be zero. So what all that particular motion of the charge particle, net velocity of charge particle will be due to ordered motion. What is ordered motion? The velocity of the rod will be the net velocity of the charge particle inside the rod, or the net velocity of the free electron inside the rod. Due to random motion, the average velocity will be zero, or the net displacement will be zero. So therefore, the random motion will not come into picture here in our discussion. What is the state of the electron? It will be having random motion, and superimposed by this, the velocity of the rod. Then which will be, when I say what is the velocity of the charge per electron inside the rod, means it should be velocity of the rod only. Because what is the average velocity due to the random motion, or average displacement will be zero, no? Or net displacement will be zero. So that random motion totally you can take it out. Okay, let's see that Lorentz force you apply. B bar into the plane velocity. So in what direction the magnetic force will act? On this, the force will be acting in this direction. Because of this force acting, the positive charge will drift, will be pushed away to the upper end. Then gradually, with after some time, what I see that there will be deposition of the positive charge. And here there will be deposition of negative charge. In fact, in practically what happens, we are sure that there is nothing called like a positive charge moment, no, because the new where do the protons with inside the nucleus? Then what is positive negative charge? Here at the lower end, the electrons will get deposited. The excess of electrons here at the lower end is what will build up negative charge. The deficiency of electrons at the upper end will build up the positive charge. Is it okay now? I'm making things clear. Don't take it another way. The deficiency of electrons is what here? Positive charge. Here, deficiency of electrons is what? The negative charge. So because of this, there will be an electrostatic field is set up. A net electrostatic field is generated here. Then continuously this rod is being moved. So here the positive charge. What are the forces that will be acting on it? FB, behind electrostatic force. Yes or no? Why do this electrostatic force? Due to drifting of charges only. Now, how long this like a drifting of charges will occur? As long as DFB greater than DFE. Once the DFB is balanced by DFE, no longer the drifting of charges will occur. Then the amount of charge at the upper and lower end will remain fixed here. Then we'll get a one electric field and length is L. So there'll be a constant potential difference will be generated. Now we are trying to calculate that potential difference. So now at equilibrium, DFB is equal to DFE. So this is QVB. This should be equal to Q into E, that one. So this will be VB. What is E? We can write it as dE by dx. Only magnitude I'm taking. So further this dE is equal to VB into dx. The EMF induced E, or write BLV. In the mathematical form, we can write it as it's a triple product, no? So there's a form what the EMF induced. So EMF induced what happen? It's a scalar quantity, no? Don't write E bar. It's a potential difference. V is the velocity of the rod. B bar is the magnetic field, and L bar is the effective length. So now the moving rod will behave like a source of EMF. Then which end will be positive? The upper end will be positive. So this moving rod I can replace with a cell. The upper end will be positive, the lower end will be negative. It should be a conducting rod or non-conducting rod. Non-conducting rod, no question of any free electrons. No? So if you move a rubber rod, we don't get any potential because there are no free electrons. So what is this? Shall I call this is the deficiency of free electron? Deficiency of free electrons. What about this end? Efficiency of free electrons. So which end is positive negative? Either you can take help of this formula or directly take help of Lorentz force. Now you assume positive charge inside the rod. In what direction the positive charge will experience a Lorentz force? The thumb will be directed in the direction of the positive potential. This is called like a motional EMF. Why do this EMF is generated? Due to motion of the rod, due to translational motion of the rod. What is V? V is a translational velocity. Later we'll go for the rotational effect. So now there are only situations like this, a B bar into the plane. A rod is moving. Then which end will be positive? You assume a positive charge inside it, and it will experience a force plus minus. And same in B bar. If I move the rod in this direction, then B bar, the velocity, so this end will be positive. The field can be out of the plane. Then B bar and velocity, so this end will be positive, this will be negative. This will be positive, negative. Just assume a positive charge inside the rod. The direction in which the magnetic force experienced by the positive charge in the rod will be the positive hint. That is the best way of this one. Or else take help of this mathematics. So this is about the rod. Now the initial example, let me go for the application later on. Now the shape of the rod. Let's come for what is that L bar, effective length. So first case, I will take the rod. In all the cases, the length L is the effective length. B bar is into the plane. And in all the cases, I'll move the rod with a constant velocity V along x-axis. So let this be the 1, 2, 3, and 4. What is the EMF induced in all the cases? So what is L bar? Effective length. So what is the effective length in all cases? Will be same. So E1 equal to E2 equal to E3 equal to E4 equal to BLV. The shape of conductor, it doesn't matter. Is it okay now? I think this is really going to help you a lot. So don't get scared with some different shapes. Go for effective length. So effective length from where to where we have to calculate. From here, there's effective length, L bar. B bar velocity, so get the effective length or the shortest distance between the ends. Shortest distance, like a displacement. You look at this displacement. Displacement vector you calculate across the ends. That will be the effective length here. And what about the which end is positive, negative? So again, assume positive charge inside the conductor. So this end will be positive, negative, positive, negative. Now, if I move a loop, okay, this is okay. Now, if I move a loop itself, that the uniform man field is there. Say very rather than numericals, no, when you are learning itself, just see that let the radius of this be E. There's the iron ring. There's a B bar. I'll move in a uniform magnetic field. The field is uniform. What to do, like how to get the it was rod, no, little bit easy for us. Now you do one thing, break up this 1, 2, 3, and 4. 1, 2, 3 is what? One ring, semicircular rod, and effective length will be how much equal to 2a, and this also 2a. So this is equivalent to like a two cells, and they're moving with a speed v. What is EMF? This will be E123, and this will be E143. And what about magnitude of both? Will be equal. How much it is equal to? B effective length 2a into v. So how you replace suddenly with these two? So this part of the ring, semicircular ring, no? What is the effective length? Will be 2a diameter. So BV into 2a. Even this also effective length. How much the effective length of this will be 2a. So BV into 2a. Then how to give polarity? You assume here positive charge. All of you see left hand. Fleming's left hand rule is very important. See all these things not by seeing. Your left hand should be free. F equal to BIL, then F equal to Q, V bar cross B bar, the left hand should come. When you're using cross product, the right hand should come. If you twist your arm, there should be a pain in your left arm. Then only you are learning EMI chapter. Left hand what pain? Another 2 weeks, a pain should come. You should apply the Zendo bomb. Where to apply that one? Your arm. This one, the ear, no, exactly at this turning point. So at the fist water pen, you should apply the Zendo bomb because almost every problem needs Fleming's left hand rule, F equal to Q V bar cross B bar, E equal to V bar cross V bar dot L bar. So if there is a pain in there, as you have put effort. If there is no pain, then okay, finish. You'll become accountant, not engineer. Don't see things. No, the left hand should be there. So now take left hand. Let there be a charge here. Put positive charge. Put finger B bar in the direction of the ring, in the direction of B bar. The pointing finger, thumb, pointing finger, middle finger. I think this everyone knows. So now put that one. Then open middle finger in the direction of velocity. Look at the force. The thumb will point upward, no? So the thumb will point in the direction of positive potential. So therefore the upper end is positive. So directly you can give the polarity. This will be